I enjoyed what you call it. Huh? I enjoyed what you call it.
I had to get it.
Yeah, it's you.
Fuck, 20 minutes, that's nothing.
You spoke Holland? You were halfway through your speech before you hit your content slot.
Yeah, I know.
So in this way, the talk, this is going to be a fast talk, but I'm trying to give you a taste of something I wish someone told me a very long time ago about how the way it works.
Sorry.
To most out of this game. A lot of people use R but don't understand what they're doing. I think. Well, they do understand it as well. It's a cliche. It's really a good sense for how to use in the language, and it also works for that. So I think I'm going to go through the design of R. I think R is a lot of different things to a lot of different people. Okay, and I'll give you a motivation as to why you should know about what I'm going to tell you. It's a big secret, big surprise. We'll go through some examples if we've got time at the end discussion. Yeah. Okay. So for a lot of people, this is R. I took a screenshot of my R workspace. It's a complete mess. You can see way too many global variables, using it all wrong, disgusting, right? This is not R. If you're a bit older, you might think this is R, right? Because before RStudio, there was the R GUI, but this is also not R. R is that little bit at the bottom. Sorry, my talk is only about R. I don't talk, there's not much else to talk about yet. It's an R conference, right? So I don't have data or fancy results to show you. We're just going to talk about how you would use R, the programming language itself. So that little, that forward arrow there, that inequality sign, that's actually where R starts, right? So if you look at it at a high level, you might be using RStudio or the R GUI, and that's the bits at the top, right? So you're not really at R yet. What you're really doing is you're using the command line interface into R, okay? And underneath that, you're actually calling the R interpreter. So people will say, oh, you know, your R code's not fast, or oh, R's not performant, or R runs out of memory. Or, there's a sort of theme of complaints happening here, but there's something that happens under that interpreter layer, which is really, really juicy, which is the R core, right, which is made up of two primary languages. It's mostly C libraries and Fortran libraries. And this is important to know because a lot of very clever people have been working on this thing called BLAS, LAPACK, GSL. There's a whole bunch of libraries which are super well established. So if you want to do, for example, okay, so when we use R, we use a lot of vectors. There's a reason for that. Vectorized operations in R are highly, highly optimized. Like you will not be able to do vector operations better than those libraries at the bottom. BLAS is the basic linear algebra subprograms, LAPACK, linear algebra pack. So every time you do a matrix multiplication, you're actually calling LAPACK. Every time you sum a vector, you're calling BLAS. And every time you call the optimum function to, let's say, solve a logistic regression at scale, you're actually calling the GSL, one of the subprograms in GSL. So this is really important to know because what most people end up doing is putting most of their workload in R somewhere near the top there, right? Which is not ideal because it's not what the library is actually designed for. So how you use R really matters. You can embed it in applications. It's GNU. You can just pull it in if you want. Alternatively, you can use the interpreter, which is the way most of us use it, which is great. R is super interactive. You punch lines of code into it. You get feedback. You can visualize it. It feels like a conversation, right? And that's excellent because what you don't want to be is a coder who complains about how long his code takes to compile, unless it helps you explain why you took so long to do something. All right, so R is hugely optimized there at the bottom. Not to say it's not hugely optimized at the top, but the problem is that there's a lot of very scary operations that typically end up happening at the top, which you want to avoid. So I'll give you a good example. Every time we get an intern, we give them something to do in R, right? And the first thing that they do is they go and write a loop. So they want to sum something. So obviously, you know, you're new to the language. You haven't had the tutelage from Jenny or someone who's really experienced. And the first thing you do is you write a loop, right? So I've seen a lot of I loops in this talk, and loops keep coming up a lot, and everyone's like, ooh, avoid loops, but why? So when you write a loop, we're just going to loop through, let's say, 1 million objects over here. It's not that big a number. It might feel like a big number, but 1 million objects for a modern CPU is pretty small. So you loop through this list, and you sum j and just add 1 to j. And you check, well, how long does that take? You're like, oh, 360 milliseconds. You're like, oh, that is so fast. You're like, yes, it really is. It's super quick, considering the damaging code that you've written. Because what's happening is R starts off, and it says, you push that first line, which says j is 0. So it goes, okay, we're assigning 0 to j. Does j exist? Does it not exist? Do we have to open up in a register? What are we going to, okay, we're going to make it 0, and what is 0? 0 is a number. Cool, let's give it some sort of memory space for a number, right? Because it's interpreting what you've given it. The next line, it says, well, you want a loop, right? So we're going to go and we're going to make a loop. What's the loop? Oh, it's this 1 million objects. Okay, create 1 million objects. Poof, creates 1 million objects. And now it starts to iterate through them because it's picked up you want an iterator. Then it sees j equals j plus 1. It says, what are we going to do? We're going to add 1 to j. What is j? Oh, j is over here. Okay, cool. Let's take a value there, add 1, put it back in. And it hits the next part of the loop, and it goes, oh, we've got j. And it's like, now it's stuck in a loop, right? So it's reinterpreting that same line 1,000,000 times. And this is why your R code is slow. It's because the interpreters constantly have to re-understand that one line. It's not compiling it up front. It's not going to make an assumption. It's not going to dynamically embed that function once off. It doesn't interpret once and recall. Okay, if it doesn't interpret once, it hashes it, but still, there's a lookup there, right? So this is really impressive, that it did 1,000,000 interpretations in 1/3 of a second. Very cool. But it's not good, right? Because you shouldn't write a loop. You shouldn't be doing that. You should say, you really want to sum 1,000,000 ones, make a vector of 1,000,000 ones, and then hit the sum button, right? So this is a vectorized operation. It is trivial in R. It takes less than 1/10 of a second, so it just rounds down to 0. You can use the micro benchmark framework if you want to get really fancy. But the point is that we phrased it wrong to R, right? The way that we presented the problem was incorrect. But sometimes loops, you just can't avoid them, right? So the first advice you give the intern is you say, well, just don't use a loop. And then they look at you like you've fallen out of a tree. Like, how on earth could you possibly do this thing without writing a loop? And then you tell them, well, there's this thing called apply, right? So whether it's sapply, lapply, vapply, some sort of apply, and now you really break their brains because they go and they see this thing called functional programming and have absolutely no idea what to do with this. And they're very upset with you and they think you're just trying to make their life miserable. That comment about avoiding deep recursions is also important. We do a lot of prescriptive analytics where I work. And recursions are really, implicit recursions are often a really nice way to solve a problem, especially when you're dealing with hard optimization problems or mathematical optimization. And it's nice to prototype in R, but sometimes you need that last punt of performance, and now you're spending all the time in the interpreter instead of just getting through this tree. So that's a bit frustrating, but yes, so we're getting to the good parts. The next piece of advice is you say, well, only use vectors, right? And now everything must just be a vector, and R we know is optimized for vectors. We've spoken about it. So you think that this is going to be an okay approach, but there's some data structures that just don't work as vectors, right? Sometimes you want a different kind of data structure to perform a particular kind of task. So examples of this, KD trees, R is abysmal when it comes to doing spatial lookups. It's really not quick. If you need a priority queue, there's no such concept in native R. Priority queue is also really useful. I'm going to give you an example about that. But there's tons. I mean, there's a big algorithmic toolbox that's missing from R because it's geared more for data science than for just a general purpose programming. The last option, which no one wants to talk about, is you can work in Python. I say lol to that. I refuse to work in Python. Python's not cool at all. R's where it's at. Okay, so I had a deadline for this presentation, which was the 16th. So what I did was I had a look at what the most popular packages are on CRAN. There are 10,000, as it turns out, which is really amazing. I'm pretty sure 10 years ago there weren't this many packages or this much popularity in R. But none of these packages are not equally popular. So we're going to organize them alphabetically. There are no names here, you can't see what they are. From left to right, these are all the packages. And you can see there's a package right up at their top, streaks ahead of everyone else, right? With over 100,000 downloads in 2 weeks, right? Super cool, right? And down here at the bottom, you've got the sort of, let's say the bottom feeders of the package society with like maybe 1 download. Shame, we feel bad. It's not so good. But there's this like ecosystem here in the middle, which is pretty cool, right? And, okay, so who wants to guess what the top package is? We have any takers? Someone's going to say ggplot, and someone else is going to say ggplot. Okay, do we have a dplyr? Okay, we've got a plyr anywhere. Oh, CPP, beautiful. So now, the one package no one's spoken about today is at the top of this list, right? And this is kind of important. And I saw this on a R bloggers download thing, and I verified it for myself because depending where you look on the internet, people will tell you other packages are number 1 on CRAN, which is all a lie. So this is the canonical source as of the 16th. But what's important here is there's big dependencies between these libraries, right? So if you're pulling down ggplot, you're also pulling down digest. If you're pulling, and I think plyr, you need the magritte for that pipe operator. So there's like big interplay between all the packages, but somehow RCPP's got the biggest overlap with all of them. And there's a fundamental reason why, which is that you can now build optimized C, C++ code using RCPP native to the platform that the code's actually going to. So this is kind of important. So if you're on Windows, for example, and you download dplyr, it's a really quick download, okay, depending on your internet speed, let's say maybe 10 seconds, and then it loads and you're done. And then you go work on Unix and you download dplyr, and you go make a cup of coffee and you come back like 15 minutes later because it compiles everything from source for the platform that you're on. So if I'm on Ubuntu, it looks at the source code and says, this is how we really get the most out of dplyr in your system because it's actually a C++ library. Okay, so that's something that's worth knowing. So Windows, obviously, there's a platform, a standard for the platform, so they can build it once and distribute those libraries. So the question is, you're asking yourself, well, geez, if someone's doing stuff in RCPP, and a lot of people are doing stuff in RCPP, there must be some sort of benefit to you getting into this sort of ecosystem. How hard can it be? And I think if you're going to use RStudio as a barometer for anything, the fact that they've got a little RCPP drop-down over there, in RStudio you can make an R file, but you can also make a CPP file, right? So that's really cool, because they're saying, oh, this is so fundamental to the way that the really productive people work in R, that obviously we must just give them a link to create C++ files. Duh. So yeah, you can do this, and you get this, which is great. It's this perfect little startup file. It includes a header so that you don't forget your header, to make sure to bring in this nice library that maps everything between C++ and R. You can make, so they give you a nice little example. You have to put this RCPP export to tell it to export this function to R so that you can use it. Okay. So we're going to write a little function. We're going to run that same function that we wrote before, except we're going to write it out again in C++. It looks almost identical. I mean, we've had to create the loop, which is a pretty normal C++ thing to do. And we say, add this up 1,000,000 times and give me a result. So we benchmark this function. So you start by sourcing it. So you say, compile this file. It compiles it. It brings in the method into RLand. And then you call this function, right? And it gives us 1,000,000, which is the correct result. Whew, huge relief. Okay. And when we check how long it takes 0 seconds. So now we've written a loop that we've called from R with our data from R in the place where we like to work, but we've managed to get the performance of another language that we've sort of dynamically compiled in. I've lied though, which is that little compile step took 5 seconds, right? So that's not so cool, because to actually build that function that can run really, really quickly took a while. So now it's all about the trade-off, right? If you're calling it once and it takes a little while to run, you don't really care. If you're calling it lots at scale, or it's a really big operation, now you don't mind 5 seconds of overhead if the process takes 5 hours to run. So that's really important. And gotchas to watch out for, because you're now working in C++, size matters. So as an example, if our sumlots function read sort of 100 billion, all of a sudden RStudio, which is really crazy, underlines that inequality sign for you, which is super cool, because it tells you that actually you've got a problem here. You have an infinite loop, right? And it might not be obvious why, but the keen-eyed person will notice that int over there is a 32-bit int. It's signed, which means you have 31 bits of accuracy, which means you can do about 2 billion, which is a fifth of the number on the right. And every time it gets to the top end of the number it can represent, it rolls over and becomes negative again. And then starts adding all the way up and then rolls around again. And so it goes. And then eventually you have to kill your R session because you broke it. So there's a problem, right? You can really break R now in a very fundamental way. But you can also use R in the way that you were using it before. So you can still use all the vector operations in C++. They've wrapped all these things for you. It's called RCPP sugar because it's sweet. Okay. So, yeah, this is fun. So what you get for your ECVITs, right? So you're going to put in some time, you're going to understand this, you've got a process that you want to run like really, really quickly. You get flexibility, maximum speed. You can find out where the bottleneck is and then just optimize that function. Because like R is experimental, it's fun working with it. You don't want to be hard labor in C++ unless it's really worth it, right? So the C++ sort of library or ecosystem has this thing called the standard template library, which is a whole bunch of really well-tested algorithms. So let's say you want a priority queue. You're not going to go and invent a priority queue from scratch. You're going to use one that's already there. Okay. So I'm going to do an example on priority queues. Very useful data structure, and this is, unfortunately, please don't gloss over on me. This is really cool. You can insert with a priority. So you can have a whole bunch of items that you put into this big container like a list, and you can tell it, well, how important is this item? Now, items that are really important end up at the top of the list. Items not so important at the bottom of the list. Automatic sorting, right? And the whole point is it supports operations. This is the big O notation. Insertion is log n. So however big the list is, it's log of however big that list is. That's how much it costs to insert it. So every operation costs a little bit, right? It's pretty cheap. But what you can ask a priority queue is, who's the cheapest in the list, right? And that's order 1. It's basically free. If you try and replicate this in R, because someone told you you're not allowed to use loops, and you have to do it with a vector-based implementation, this is an error. I didn't update the slide. It can be done in order n time. I'm going to show you an order n log n time implementation, which is much more expensive, right? It's going to take a lot more time to perform these operations. But again, getmin is again also approximately free. So why would you want to use this? Well, we can go through the code if you want, but effectively you can create your own custom data structure. So you can say, I've got these pairs of values, which are my indexes, and doubles, which are the value I wanted to rank on. I can tell it exactly how I want to rank it, and I'm just going to throw data from R at this little function. I think the slides will be up, so if you're interested to have a look at it, it's a really simple way to map the STL library into R. And this is what we're going to do. We're going to take items, we're going to make a big list of items, we're going to push items in, grab the item at the bottom, change it some way, like randomly modify that value and throw it back in. And we're going to keep going until we've eaten up some number of those values, right? And this is really important. Let's say you're modeling a queue, where you're doing a simulation of people moving through a shopping center. Every time they get to the front of the queue, they randomly jump back to other point in the queue, right? Until everyone's not waiting that long or something. So this is really important. RCPP has massive usage in Monte Carlo simulations, MCMC, lots of really cool stuff. Gibbs sampling is a good example on the internet for that. So this is what it looks like. We're going to make a distribution of values. We're going to make about 100,000 of them. We're going to throw them into a list, into this priority queue. And then in R, what we're going to do is every time we get the top value, we're just going to grab it out, the minimum value on the left. If it's less than 2, we're going to throw it back into the middle. And we're going to keep going until we've covered everything less than 2. So effectively eating from the left of the distribution and throwing stuff back in on the right. Okay? But we're throwing it back in randomly. We don't know exactly where it's going to fall, but we're just going to keep processing this object, right? And you do this, it's about 3,600 iterations to eat up everything less than 2, so everything to the left of the line. And that takes about 7.8 seconds. Maybe you're happy with that. I'm not so happy with that. Because every time that we go through this iteration, we have to resort this whole list because R doesn't allow us to just insert it where would be the perfect place to insert it, right? But we have this priority queue, right? And the code looks almost the same. We're going to go through, we're going to take the item off the left, we're going to add it back to the queue. When we're done with this whole thing, we've eaten up everything to the left of -2. We've added all, you can see now the distribution looks jagged and weird, not how we would expect it, which is the whole point. You're simulating some sort of wacky process. And we add it back to the queue, we pop the queue, and we just keep processing this thing. Except now, when we run this code, same number of iterations, people take statistically the same. Except previously where we were looking at 8 seconds, we're now looking at 0.04 seconds, which is really, really quick, right? And it's a lot of objects. You're dealing with like 100,000 objects. It's complex operations. And now that 0.04 might seem a little bit unappealing, but that's actually just the R interpreter. So we've left a little bit of R scaffolding in R itself so that we can link up all those methods dynamically. A little bit of interpretation, but all the work's actually happening under the hood now in an optimized language. So this is pretty cool, right? We like this. I was going to give you an example. There's a cool Kaggle competition that happened a couple of years ago with, you had to solve a traveling salesman problem, actually 2 traveling salesman problems, not using any edges between the 2 graphs. It's fun if you like combinatorics. But this is a really big graph. And the downside with this is there were about 150,000 points. If you use any kind of out-the-box heuristic for solving this problem, you're looking at log n squared operations, n squared log n. Which is 280 billion operations. That's more than your computer can do in C++, right? So now you've got to rethink your approach. So priority queues are a great way to solve this. If you're looking for a fun exercise to take away from here and do at home, that's, not that I want to give you homework, but this is where it really starts to get into its own, which is quite cool. So I think we're going to leave a little bit of time for questions, but there's 3 things I want you to take away from this, which is 1, it's easier than you'd expect. 2, if it's good enough for Hadley, it's good enough for you. I think that's a really strong principle to go with. If you read his blog, his sort of memo notes at the bottom say, I'm so grateful to this person for twisting my arm and forcing me to learn this because it's too cool, right? And lastly, if you're talking about scale, these functions all deploy in a scalable way. So if you're using an infrastructure like Spark as your executor system for doing these big analyses, you can have your bespoke functions embedded in distributed processes. So now, you effectively get a double win. It's really cool. So if you want to know more, you can drop me a mail or chat. That's great. Thanks very much. On time. Good.
Any questions for the speaker?
So if you want to learn more and get better at writing optimal R code, so like where do you start?
So I don't think there's such a thing as optimal R code. You can get good at it and you can do a lot, but I don't think R is ever perfect. You have to sort of draw a line in the sand and say it's good enough. But when you, at that step in RStudio is super cool. They know that you're going to ask that question before you ask it. So we're just going to go back here. When you create a new C++ file in RStudio, they are super cool and they give you 3 very important links right there in that file that they created. And those links I would say that is the source truth of how you should aim to code in C++ if you're looking to make an optimized process. And then the STL reference is also really useful. So just look at the standard template library and how they implement things. And if you can basically do the same thing in R. It's very cool.
Okay.
Oh, there's one more.
So when you're actually doing something that's in a vectorized way, it's still doing like different between like in a loop, just doing something like class or address or the that, something that's like not more well, it's negative.
Can you say the question again so I make sure I answer the right one?
Like, what I mean is, you do something like that example, like when you sum from 1 to a billion, especially do that in like vectorized approach, right? I mean, it's still implemented like maybe not in a function, but it's still like in a sort of imperative way. Like it still does it iteratively, but it's like it's implemented like further down in the next picture that you showed earlier.
100%, yeah. Then it's right at the bottom. I think a good example of this is where you've got to be very careful now because you've got this great tool at your disposal. You think like, oh, I should go and implement some of these functions myself. Don't do that. Because if you take like matrix operations, really subtle, right? So matrix multiplication, the way you do it at university, it's this laborious process and you get out into the real world and someone hands you two matrices to multiply together and you think, oh, I'll just do it the way I was taught. Bad idea. That's n cubed operation time. It can be done like theoretically in n to the 2.43 or something now. But right down there in the bottom of R, they've got that covered. Like just leave it to the professionals and like stay further up the chain if you can. But yeah, if you need to iterate though, you can. So what's quite nice is Hadley gives a good example of what the overhead is of using the RCPP sugar to make sure you don't mess something up so they do the type inference for you. And it costs 2 nanoseconds per iterator on the overheads. So it's really optimized and it's really, really quick. So it doesn't hurt that much now, which is, yeah, it's useful to know. So I think read quite a bit about it and then see exactly what level it makes sense. And then try not to code a lot. Yeah. Cool. Thanks.